Today we're going to be practicing conservation of momentum questions. And we're going to be talking about the property of conservation of momentum as it pertains to collisions. So a collision, quite simply, is any time one object comes into contact with another. That's a collision. Anytime two objects interact through Newton's third law, through contact, we have a collision. So I can state it a bunch of different ways, but for us, we're going to try and control the conditions of a collision so we can take measurement. So actually, let me change that real quick because we have two specific colors here. Let's try and stick with those colors. One of those is clearly yellow and the other one is clearly green, correct? The thing we ended on was this idea that if we have a collision, say, that's going to occur, where one cart's going to strike another, the momentum of these two carts, momentum of the yellow cart plus the momentum of the green cart before they collide, is going to stay the same after they collide. So if this is the before collision part, then I don't know what's going to happen during the collision. I mean, we're going to do some tests to see. But I'm going to assume that after the collision, the cars are likely moving, but moving different than they were before. You know, I would expect that this car is probably going to have less momentum than it had before, and I'm going to expect that this car probably has momentum now. That seems like a reasonable outcome here. Would you guys agree? Now, what we talked about yesterday is that after they collide, so this is where the collision occurs, the momentum of the yellow car plus the momentum of the green car will have to be equal to the momentum before they collided. So if this represents the after and this represents the before, we add up their momentums, they have to be equal. And what we're going to do here in a minute is we're going to do some collisions and analyze the data and see if we're close. So for this example today, each car is 0.286 kilograms. And the cars are identical, so they have the same mass. But I've also brought extra weights up here, so we'll be able to manipulate the mass of the cars. So let's start with a straightforward collision. I'm just going to do it here because it's a little easier to write it all out. So the yellow car was 0.286 times 0.76 meters per second. The green car had zero momentum. And when I put like an equal sign with a question mark over it, is we're looking to see if they're equal. We don't know if they are, but we suspect they should be or should be close. So after the collision, the 0.286 car was traveling at 0.1 meter per second, but the green car, 0.286, was traveling at 0.63 meters per second. All right, I'll give you guys a moment to try and to use your calculators to work that out, because I don't want to use my calculator to work that out. So it looks like I can call on 3 different people to give me 3 different values. So go at it, please. All right, so what was the momentum of the system before? What's the 0.286 times 0.76? 0.217. That's kilograms meters per second. We want to see if this is equal to what's on the other side, so I'll do this one, 0.0286. What's 0.286 times 0.63? 0.208. Okie doke.
Oh, wait, no. That's what I got as my... No, sorry. That's not what I got for that.
Okay, which one is wrong?
Mine. Don't use it. Yeah.
What should I write there instead? 0.18. 0.1808. That's a lot of decimals. Okay, yay. So I'm assuming you added these two up on that right side already. We'll do so. 0.20 what? And this side is 0.217. Now, not equal. However, are they close? Yeah, I mean, if this were a lab and I wanted to try and figure out, well, how close are they? There are ways to do that. So do you guys know different ways to measure how close two things are or how far apart they are? The way we would do this in a lab is something called percent difference. So who has done percent difference before? Okay, so you're aware of how to do it. It's not particularly hard to do. We're going to learn to do it right now. We're going to calculate the percent difference. Ready? It's pretty easy to do. So you take your two numbers, and we subtract them, but we don't care if it's positive or negative, so we take the absolute value. You guys have used absolute value bars before, right? And we don't know which momentum is the correct one, so you either choose the initial value to put in the denominator or you choose the average. We should choose the average. So you have to average those two numbers. Do you guys know how to calculate a quick average? You'll add them together and divide by 2. So because I want to be a part of this today, 0.217 plus 0.208, and I get 0.213. Now, you express this answer as a percentage. So I'll take my 0.217 minus 0.208. I get 0.009 divided by 0.213. And this tells me they are off by 4.2%. That is well within, I would say, legitimate experimental error to have a 4% difference. I think you could, as a scientist, say it appears that we conserved momentum here. You understand, in science, this is not an unreasonable thing to do. Right? Now, you're making a judgment call here. As a scientist, you have to decide what you think an appropriate threshold is. Now, in science, we do have acceptable thresholds. That is what statistics is about. So you guys who are taking AP Stat, you're learning about this. You're learning about how to determine whether two numbers are far enough apart to be considered separate, or if they're close enough together to be considered the same. You guys done that kind of stuff yet? Yeah. Like a dual peaked histogram, finding out whether the peaks are too far enough apart for them to be considered two separate numbers. That's why statistics exists. And of course, you have Miss Trainham, so I know you're getting a great education. She does a good job over there. So, by the way, the general collision is what's known as an inelastic collision. Now, I don't know for sure if this is an inelastic collision. In an inelastic collision, momentum is conserved because momentum is conserved in all collisions. But in most collisions, which are inelastic collisions, kinetic energy is lost. It's converted to something else. So the general collision that we see in nature tends to be an inelastic collision. Momentum is conserved, kinetic energy is not. Now, you can test to see if kinetic energy was lost. You guys are aware of how to calculate kinetic energy, 1/2 mv squared. And you can use the information we have to compare the kinetic energy before with the kinetic energy after. If kinetic energy is lost, then the system had an inelastic collision. Now, you can probably imagine that there are collisions called elastic collisions. In an elastic collision, kinetic energy is not lost. The kinetic energy is conserved. In nature, those are very rare. Most collisions don't conserve energy. you can clearly see where I pushed the car, right? So over here, this is me pushing the car, giving it velocity. There's the car traveling towards the collision. It looks like it's going just a little bit over 0.8 meters per second. But during the collision, which it looks like the collision lasted for about the same amount of time. Did you see that? It goes from 1.2 to 1.4. So the collision's lasting still about 0.2 seconds. The car reverses direction and now is traveling backwards at negative 0.2 meters per second. At the same time, the target car, not moving at all, moves up to 0.4 meters per second. Now, I don't think we have to do the math here. I think you guys are okay with what we've seen, but do you see that we have a bigger change in velocity for this car because it was a smaller car, its mass was less, and the bigger car had a smaller change in velocity, its mass was more, it was less affected. Now, let's go ahead and do a little bit of the math real quick, all right? Because I think it's worth it. Right here, this was 0.286, the mass of this car. And right before the collision, it looks to be at about 0.8 meters per second. This is the momentum of the system. Somebody rattle that off real quick. 0.2288. Now, after the collision, we added 500 grams to the 286 gram car. So that's 0.786. And it's got a velocity that's just under 0.4. So I'm going to say, well, and this is 0.3. So that's probably 0.38. Would you guys agree with that? And now I'm looking at the yellow car. This is negative 0.2. So this line is negative 0.2. The yellow car's got 0.286. And the velocity is just a little over 0.2. So I'm going to say 0.22. Negative 0.22. All right. So, see if we can't get those out there. So this is what, 0.2 something? Maybe 0.3, I don't know. I'm going to need you guys. That's the bottom one here?
Yeah. Sorry.
That's right. Negative 0.0572. What's this top one? 0.786 times 0.38? All right. So I think we do a quick comparison, can't we? 0.298 minus 0.0572. So when I add this and this together, I get 0.241. And we're comparing that with 0.2288. So this looks like there's more momentum afterwards. We know there's not really, right? But again, we're looking to see if we're within our margin of error. So I'm going to just run the numbers real quick. 0.2288 minus 0.241. And 0.2288 plus 0.241 divided by 2, 0.2349. Five 0.2%. I'd say we're still well within a reasonable margin of error. Wouldn't you guys? Now, before you guys hear me talk about this not infrequently, but this part is not lost on me as I ride my bike every day, or try to. And it was cold this morning. It was certainly cold. But I'm getting a device today that'll arrive in the mail that will allow me to detect cars that are coming up behind me if I can't see them in my mirrors. Because I'm afraid I'm going to get hit someday. And there's been some close passes. We're talking about this already. The light car hits the heavy car, it just bounces off, right? Well, let's reverse it. The heavy car hitting the light car. The graph was a little incomplete, but I think it's good enough for us to use since we're going to run out of time. So let's bring this one over. Although we're seeing the changes that we expect, the yellow car having a smaller change in velocity because it was 3 times heavier, and the green car having a huge change in velocity because it was a third the mass. When you're driving, electric cars are heavy, and we're seeing more electrification of the roadway. A Rivian or a Ford F-150 Lightning is half again more massive than its gasoline counterparts. The Rivian is running around 7,000 pounds, and the Ford F-150 Lightning is more than that. There's now an electrified hybrid Hummer on the streets that's running around 8,600 pounds. These cars are massive, and you don't understand, we tend to measure trucks that way. There's a bridge in my neighborhood that's not rated for some of these cars to drive over. It was originally, warning signs were put up to prevent loaded trucks from going across them, but the batteries of these vehicles are very heavy. And unlike the gasoline cars, where generally the gas tank is in the rear of the car and slowly gets lighter over time as you burn gas, 60 gallons of gas is heavy. The batteries stay the same mass the whole time in the car, and they're distributed throughout the car. So although there are benefits, you do have to understand the cars on the roads are getting heavier, and their effects during car accidents are also being seen. That's why they're more costly to insure. Now, we're not talking about the little four-door Teslas and stuff like that. They are not nearly as disproportionate to their counterparts. So if you're replacing a Honda Accord with a battery-powered Honda Accord, you're not really seeing much of a mass difference. But when you start to push around an SUV, it takes a lot more battery power to do so. Does that make sense? That's why those cars are getting so heavy and so quick. Just keep in mind, these accident things, this is what's happening in the car. There's nothing you can do about it. Now, we talked about the idea that when you're driving in a vehicle, vehicles today are way more safe than any vehicle in the past. The first thing that happens in a car accident doesn't usually involve you, it involves the car. So who's been in a car accident that was over 30 miles an hour? Is there anybody? A couple of you? All right. So one of the safest things about cars now is all outside the car. That's a car. Promise. Before you guys ever enter into the car, cars today, they almost fall apart when they get hit in an accident. Parts just fly off them, bumper covers come right off. They collapse into nothing. A car in the 40s and 50s, you might ding the bumper. It was an all steel frame and all steel bumpers and steel body parts. You get an accident with one of those, yeah, the bumper would be damaged, but the car would likely survive. The occupants, not so much, but the car would likely survive. Today's car, they're dropping the front of the car down. So most cars slope more dramatically than they used to. That's not accidental. That's to protect pedestrians. It's felt that it's safer for pedestrians to go over the top of the car than under the car. So by bringing down the front end of the car, they're making the car safer for pedestrians to survive in a pedestrian accident. That's why the Jeep Wrangler went from an inline 6 engine to a V6. By making the engine shorter, they could slope the hood more. Now, all we've done is buy these cars and jack them back up. So we're bringing the hood back up by jacking them up an extra 4 or 5 inches. but the goal was to make them safer for things on the outside of the car. But also, cars are designed to crumple. That crumpling means that they are becoming part of the accident before you, increasing the length of time it takes for the car to actually come to rest. Half of a car accident now takes place outside the car. Let me say that different. Half of your part in a car accident takes place outside the car as the car crumples around you. Then you engage your safety equipment to bring you to rest. This has taken the amount of time it takes for a car to stop and made it almost 100 times longer. And we're talking about milliseconds, but it's taking almost 100 times longer for you guys to stop than it used to be when cars were made out of nothing but steel everything. The multi-body design of these cars with unilateral construction makes them nearly impossible to fix after a car accident, but makes the accidents way more survivable than they ever were before. Not to mention they've changed the whole structure of your seat too. Who's ever read the book in your car about how to set up your chair? It's multiple pages. The safety equipment just to set the back headrest in the exact right location to prevent whiplash. Most of you don't know that, but they are perfectly designed so they can be right at the exact space. And it's not the same for every person. So you're supposed to adjust the headrest and the seat when you get in there to ensure that you won't have whiplash due to any kind of accident that would cause you to hit the back of the chair. Chairs used to stop midway above your back in the 50s and 60s. So the chair's coming up behind your head is not new for you guys, but is yet one more safety advantage that these cars have that we didn't have all the time. Cars before and after the collision. So their attempt to make the cars have the same color to match their the car's colors is what we're looking at here. So the yellow one represents the yellow car, and this is supposed to be green, but not very much. So first, does that match what we saw? I mean, this is me pushing the car here, and then here's where the car was traveling before the collision, and then this interval, which is from 0.8 seconds to 1 second. That took place in 0.2 seconds was how long the collision occurred. And it looks like the yellow car slowed down quite a bit, but the green car wasn't moving at all before the collision, and then the green car had a velocity after the collision. Does that all look reasonable? Well, we should be able to determine whether momentum was conserved during this collision by looking at both the mass and velocity of the cars. So remember, both cars have a mass of 0.286 kilograms. And if we just look at the graph, we should be able to read off what the velocity was. So I'll do my best here to try and read it off, because you'll notice the car was slowing down a little bit. But I have you guys here, so you can help. Let me line this up. I'd say that probably represents the velocity of the car, like somewhere in the middle. Clearly between 0.7 and 0.8, so maybe 0.76. That seemed good to you. So that was the initial velocity of the yellow car before the collision, 0.76 meters per second. I'm going to try and do the same thing for after the collision. I mean, it looks like it's right on 1. Wouldn't you guys agree? So I think, well, 0.1. So I think we can say that it's 0.1 meters per second after the collision. The green car was definitely 0 before the collision. So let's see if we can't figure out what it is after the collision. You guys see that somewhere between 0.6 and 0.7? Would you, it's not quite 0.65, maybe 0.64, 0.63? I think 0.63 is probably reasonable. That all good for you guys? All right, so you have your data now. So if we were to look at this, we're saying that after the collision, the yellow car is 0.63 meters per second. Before the collision, it was 0.76 meters per second. The green car was 0 meters per second, and then after the collision was 0. Oh wait, no, I'm sorry, I wrote down the wrong spot. This is 0.63, and this was 0.1. That all look good? All right, so our job is to see if momentum was conserved. We want to find out what the momentum of the system was before. We know the mass of both cars, we know their velocities before, and we can do the same thing afterwards. So let's do it.